We're upset about burning.
Okay, any
That's
questions
awful
before we
for
get
this
rolling?
pleasure.
Okay, so, the last time I kind of got rolling on talking about symmetric and alternating groups. So. Okay, so, so something like this, and what this means is this is the function f of x equals ai plus 1, x equals ai, plus minus 1, a1 if x equals am, and x if x is not in the set. This is a cycle. If m is 2, we call it a transposition. Any guesses? How you get the inverse of this computationally? Yeah, so turn it around, right? Just run the function in reverse. And in fact, we defined last time what disjoint in fact transpositions were. And we left, the last thing I left you with, I think, is the statement that if you have any element of Sn, you can write it as a product of disjoint cycles. Of course, what you could do, you could just take any collection of functions. Functions can always be decomposed into cycles because all you have to do is start with an element and just follow it until it repeats. It's a bijection. Pick it up where something first thing isn't covered. Let's go through this one just for giggles. I always start this way, 1, just because 1's the smallest number, and you just got to be a bookkeeper here. 1, remember, composed from right to left. 1 goes to 4 to 6, and it's done. 6 goes to 7 to 1, 2, 5. 5 goes to 6 to 5 to 1, 2. And 2 does a lot of dancing here. 2 goes to 1, back to 2, on to 7. 7 goes to 4 to 2 to 3 to 5 to 1. So it closes off that cycle. And let's see, how many numbers do I use? Probably 8 of them. The first number I see that hasn't appeared yet is 3. So it pays to be organized here. 3 goes to 8, and it's done. 8 goes to 3, and to 4, and it's done. 4 goes to 5, 7, 2, to 1, to 3. And it looks like I've used all my numbers, right? What's up with that? So basically, this thing goes down into a pipe of these disjoint cycles. This one's a 5 cycle and a 3 cycle. And this algorithm always works, and that's why we have that theorem here. I'm going to appeal this corollary to this. 335. Sigma being SN and right sigma C1, C2, CK, where the CIs are disjoint cycles. So there's my unique decomposition of sigma into this. Then the order of sigma is the least common multiple of the orders of respective cycles. So, for example, the order of this element here should be 15, right? Because it's a 5 cycle and a 3 cycle, right? So this is 4, 5. This is 4, 3. Okay. Let me just briefly sketch why this is true. Believe it or not, you all have already done this there. Matter of fact. C1 and C2 are disjoint cycles. So let's just start with 2 disjoint cycles. Notice that C1, C2 is C2, C1. Right? Because the fact that they're disjoint means that they don't interfere with each other when it comes to moving the elements around, and so they commute. And if you look at the subgroup generated by C1, all the power is this, and the group generated by C2, the intersection is the identity. Because again, the cycles are disjoint, right? So there's no overlap here except for trivial overlap. Therefore, the order of C1, C2 is LCM order C1, order C2 from homework. This was a homework problem you all did. And now proceed by induction. Any questions? So for example, maximal yes. In S15, so guess maximal order of known is. I kind of put you on the spot. You got to bump around with it, right? Any guesses?
3 times 5 times 7.
Very good. And the key is what you want to do is break these down into cycles and maximize the least common multiple. So you could have, for example, 1, 2, 3, 4, 5, 6, 7, 8, 5 cycle, 9, 10, 11, 12, 13, 14, 15, 17. And that'll have 105. By the way, you ought to do a little counting. How many elements of 105 are there in S15? A lot. there's an enormous, because I can rearrange these willy-nilly, right? So there's an enormous number of these things. And I think that you could show, actually, here's kind of a fun problem. I used to put this on homework sometimes, but so it's extra credit. See if you can give an estimate for an upper bound for what the largest order of an element is in SN, right? You can use Lagrange multipliers to do this, right? So you never thought you'd use Calc 3 in an abstract algebra class, but you can do it.
On that one example you just showed, what's stopping us, like, why do we have to have 3, 5, 7? Like, what's stopping us from having cycles of different lengths? They have to
Oh,
be prime
well,
lengths, or?
Oh, no. This, in this particular case, this happens to be what maximizes, right? I mean, and you're right, I didn't give you a definitive reason. I mean, you could take an 8 cycle. Okay, so now whatever the order of this is will have a factor of 8, right? Well, you don't want to use any even cycles from now on, because it's a least common multiple thing. And so any even factor is sort of sucked into that 8, right?
Oh, okay.
And so what do you do after this? Well, you do a 3 and a 4 cycle, but that's not helpful. The four just might as well not be there,
Right.
right? And so for this one, if you want to, once you've got this, I think the best you can do is this. But it's good that you point that out, because there's subtleties, because it depends on things like prime factorizations and where they show up. So this has 56, which is not quite as good as this, right?
Yeah.
So the primes actually help you spread it out. Actually, it turns out to maximize it, that what you want to make it big is you want primes that are clumped in the middle, right? And that'll sort of help maximize in a certain sense. Let me give you another corollary. 3 from 6. Any sigma in SN is a product of transposition. Notice here, I do not use the word uniquely. And let me remark all this is true. Let me be a full, by the way, there's 2 words I didn't use. Number 1 is disjoint, and number 2 is uniquely. First of all, there's no hope of being able to write everything in SN as a product of disjoint transpositions, because what's true about the order of a product of disjoint transpositions? It's always 2, right? So, that's not going to work out for you. So, okay, the loss of the word disjoint is probably not too surprising. You're also not going to get unique. And let me be a total smart aleck on this one. That is a transposition. Which is the same as that. So I've expressed this element as 2 ways as a product of transpositions. And of course, I can go bananas with this. I'm a little bit too bananas, I'm afraid. 3, 6. Actually, I'm going to throw 3, 5 in here. By the way, I think we can all agree that this is the same as this, because those 2 cancel each other, right? But this one kind of cancels in tandem. These are dead, then these are dead, these are dead, then these are dead. It's bloodbath out here, and then these are dead, and at least in point. Now, okay, uniqueness is out the door too. Forget about it. But notice I wrote that as a single transposition, or 3, or here, I believe it's 11. Notice that I always wrote 1, 2 as an odd product of transpositions. And this is one of the most important things about this here. Let me give you the following pair, and I'm actually going to prove this for you. By the way, have you all seen this before? The proof that every element of SN is either even or odd. Some of you maybe yes, some no. Here. It's sigma in SN can be written as sigma equals tau 1, tau 2, tau m, which is, let's say, beta 1, beta 2, beta choice, K, where the tau I, beta J are transpositions. Then M is equivalent to K mod 2. That is to say, any element of SN, if I can write it, then whenever you write it as product of transpositions, then maybe different transpositions, maybe different lengths, but they'll both be even or they'll both be odd. Okay, so let me go through the proof of this, because this is kind of a simple thing. Why is this true? Well, is both even. Let's just suppose, and I haven't defined this term yet, but what I mean by even is, suppose I can write it as a product of an even number of transpositions. Suppose I can also write it as a product of an odd number of transpositions. So let me kind of put this into action here. Sigma is tau 1. And actually, I like this proof because it illustrates kind of a cool way to reduce things. Choice. Suppose that I can write sigma as this odd product transpositions here, and this even product transpositions here. Just as in the statement of theorem, my taus and betas are all transpositions. Let me point out that tau 1, tau 2, tau 2, and 4. Notice, what did I do? In all cases, I composed both sides by tau 1 to tau 2 and so forth to get this. Remember, every transposition is its own inverse, right? So I just ignored the inverse signs. Everybody okay with that? See where we're at? So let's start over then. So and now that so in other words, so my observation here is the identity is odd. And this is where I want to get my contradiction from. I want to go through this and say, well, it turns out the identity can't be odd. So it suffices to show. Okay, so I'm going to try to get a contradiction. Or a contradiction we have the identity is tau one, tau two, tau two n, m plus one. And here we will say that m is minimal. Now, let me point out, what I mean by this is, let's assume that the identity is an odd product of transpositions, and let's assume that there's at least three of them. Because, stop me if I'm wrong, is it painfully obvious to you all that the identity is not a single transposition, right? That's pretty clear, right? But I think even with three, A, B, C, D, E, F, I could probably go through and prove that three, it's not a product of three, but it's getting a little bit more of a gray area, right? And if I have 101, deep in the depths of some Stephen King novel, I could find, 101 of these transpositions that multiply together give you the identity. It's not quite clear how to sort that out, perhaps. It's not immediately clear, oh, you can't do that. It is clear for one transposition, but it's already getting a little fuzzy with three. Okay, so let's suppose that we can write sigma, or I'm sorry, the identity as a product of an odd number of transpositions. And we're assuming that that is the smallest number, right? Certainly, if you look at the number of odd numbers that you can write this as an odd number of transpositions, 3 is the smallest, and there's certainly a minimum, right? And what we're going to do is contradict these analogy. Now, to move forward, I'm going to write down a couple of computational things. So let me this one. So let's take a little time. Let's look at some computations. I'm going to need this in a moment. What I'm going to do is I'm going to move transpositions across here. And let me appoint, if I have if I ever encounter 2 of the same transposition next to each other, that's the identity. Agree? What else could I do? What if I encounter A, B, and C, D? And here in my little computations here, I'm assuming that all different letters represent different values, right? So these are 2 disjoint. Notice, actually, this way. Notice I can just turn this around. Everybody okay with that? Oh, what else could I encounter? What else could A B encounter? Well, here we had exactly the same. Here we had nothing in common. You might have one thing in common. Like that. And this becomes, let's see, I'll convert the A goes to B, B goes to C, and C better go to A, it does. And let's see, I want to make something here. So, this. A goes to C. C will take it. No, I'm gonna make it. Let's see. A goes to B, B goes to C, and C goes to A. Okay, good. That's right. And finally, if I get this, So in other words, now they have the A letter in common, if they have the B letter in common, A, C, B. That interchange B and C here. A goes to C, B goes to A. Everybody okay with it? Okay, so I think this is all the situations that I need to encounter. So now let's look at what we have. So we have E. One, tau two, tau 2m, and I'm gonna call it safety. Right. Now, there's an important thing I want you all to notice about this. My computations are defined to do this. AB encounters AB, it's dead. AB encounters CD, and it just flips out, right? AB encounters AC, and AB goes through. Notice there's no A back here. There's no A in the way, right? And the difficult one is AB encounters BC, then this out, so A goes to C. Notice there's no A in the wake anymore. There's no A back here. There's still an A here, it's just with a different companion. Right, agree with that? So I should be able to leapfrog this and this and this and this. So apply 1 through 4 as needed. Get right. So I just apply this rule, whichever one of these applies here, I'll use it and I'll just keep moving until I get a something in front. Everybody okay with that? Now, let me make an observation. Number one, if I never use 1, then no Ti prime is the identity. Because notice, let's assume first. Actually, let me just say this. Assume first. I never apply. Yeah. So I only have to use these 3 rules going through. That is, suppose that as I move this transposition from right to left, I never encounter another A whatever, right? Or never encounter the exact same thing. Then, in this case, you have the same number of transpositions, right? Because whenever you don't use 3, your input is 2 transpositions, your output is 2 transpositions. So my numbers have not changed. Are you okay with that? And this is a contradiction. Anybody tell me why? Notice, if I call this sigma, sigma of A is equal to X, right? Because there is no A in the wake. That's how we set this up, right? So if I'm going to do the computation, no A, no A, no A, A goes to X. And I don't need to know anything else to know. So sigma is not the identity, right? Because it took A to something else, mainly X. All right, okay so far. So it must be the case that we apply one at some point. Agreed? And what happens now? At that point, two transpositions cancel. Right? Because we got two of them same next to each other, they cancel, and E is the product of 2m plus 1 minus 2 transpositions. It contradicts the amount. Okay. Any questions?
Could you just repeat the thing about the sigma A equals X?
Right, because
Like, is it the
Let's
same,
call this-
is it the same sigma that we started with, or is it just a different sigma?
oh, if I call this sigma here, if I call it, yeah. So what I meant by this here is this is supposed to be the identity. I'm going to call it sigma just for convenience, right?
Oh, okay.
Right. And if you look at sigma of A, there's no A's until you get right here. So it has to take it to some X that's not A. So it can't possibly be identity.
I see.
Everybody else okay? Okay, good, good. Okay, and so now it makes sense to call these things names, and the names I'm going to call it is even or odd. So if I have some sigma in Sn, I can call it even if it's product of the even number of transpositions, and odd if it's product of an odd number of transpositions. So let me give you the students here. Proposition. 3 through 9. All n greater than or 2, an, find to be the sigma in Sn, such that the sigma is even. Wrote odd notes, I don't know why, it's so weird. Is a normal subgroup of Sn, and the number of elements is n factorial of 2, and An is the unique subgroup of index 2. Okay, let me give you at least partial proof of this. Here's kind of the slick way to do this, I think. Define phi from Sn into plus or minus 1. I think I mentioned this earlier. I wrote the group additively earlier. I'll do it multiply here. Notice, of course, plus or minus 1 is a group under multiplication. 1 times 1 is 1, minus 1 times minus 1 is 1, and so forth. Defined by d of sigma 1 if sigma is even, and minus 1 sigma is odd. Notice that d of sigma 1 sigma 2 is d sigma 1 d sigma 2. Let me talk you through this. Notice that if you have the product of two odd transposition or two odd permutations, then it's even, right? Because when you add two odds together, you get an even. And notice if you have an odd times an even or an even times an odd, you get an odd, and the product of two evens is an even. And basically, that's what you need there for this to be a homomorphism. That works out for you. Notice that P is on to. So, well, let me see, and so kernel of P is normal in Sn. And the kernel of P is, of course, the set of sigma in Sn, which sigma is even. Which is 8. So now we have that AN is normal in Sn. Because, of course, the kernel is always a normal subgroup, and AN is the kernel of this. And my first isomorphism theorem Sn by AN is isomorphic to this group here. And so now it's just a simple counting argument. This means the order of Sn divided by the order of AN. So the order of AN is impact. I will leave the unique subgroup of index 2 as an exercise. The uniqueness part. Okay. Any questions? Okay, so here's I'm just going to write this theorem down. This is what we're working toward. I think most of you know this theorem, but we're going to actually prove it. It's simple. It can only let me recall for you what it means to be simple. It means that you have no normal subgroups in the group except for the identity and the entirety itself. And this is actually a very important source of simple groups. In fact, the easiest source of simple groups are groups of order prime, right? But they're kind of silly. They're cyclic and prime order. They're only subgroups for themselves in the whole thing. So it's kind of beyond them. Well, so let's go through it. A2 is silly, it's the identity. A3 is cyclic of order 3, right? Because this right here, it should be 3 factorial over 2, so order 3, again, is prime order. A4 is not simple. A5 is order 60, and that is actually the smallest. That is the smallest simple group. It's not really. By the way, just for giggles, does anybody? How many of you knew that A5 was the smallest simple group that's not theory? That's the smallest one. The second smallest one is the order. Anybody know what the order of the second smallest one is? Yeah, it is big. Of course, the next stop on the simple train is what? A6, which has like order 360. but there's actually a group for 168. It's 3x3 matrix, you can fill two elements. I think it's about 168. But let's prove this. To prove this, it's kind of computational. It's kind of fun. So we're going to introduce a couple of lemata here. And this first limit I'm going to give you is sort of independent interest, if you will. Tell you some interesting stuff about the structure of the symmetric and alternating groups. Here, let and set 1, 2 up to n be distinct. Then an is generated by all 3 cycles. RSK. Right. And of course, K is not equal to RS, RS. So for example, this is really kind of cool because what this says is even if you've got a 1 million, right? Even if there's a whole bunch of numbers there, you got a 1 million, pick 2 distinct elements between 1 and a million, say 1 and 2, then this says that a 1 million is generated by 1, 2, 3, 1, 2, 4, 1, 2, 5, all the way up to 1, 2 million, which is kind of cool. So let's see why this is true. Note RSK, and here remember RS and K are distinct, is in the form by the way, I know I've said some of this to you in my office when you're talking about homework and such, but remember, this is kind of an important thing to remember. Any odd cycle is an even transposition, and any even cycle is an odd transposition, right? Because basically you can take any cycle, this generalizes to any n cycle, you can break it up as R last, R second to last, all the way up to R next to it. And that will give you one less cycle than, or one less transposition than the length of the cycle, right? So first observation, 3 cycles, they're in AN. So the group generated by RSK, where is a subgroup of AN. Right? The interesting part is that you get it the other direction. Let me point out, so how do we know we get it all? So for the other containment, observe that every element of AN is a product of elements of AN. Got a couple of forms I can write down. Or, let's see, so they've got 1 in common, 1 and 2 in common. We have nothing. Here, A, B, and C are distinct. How do I know this? Well, I know that any element of Sn is a product of transpositions, correct? So any element of An is a product of an even number of transpositions. And so basically, think of it this way. Your two transpositions could have one thing in common, or they can have nothing in common. Right? By the way, if they have everything in common, that collapses down to the identity, but you don't need that separately, because notice, if you take this element and multiply it by itself, or that one by itself, well, not that. If you take this one and multiply it by itself, you get the identity. Right? So now all we got to do is show that we can come up with all this. So what an alphabet soup here. So to that effect, notice what is A, right? Okay, so let's let Jim put his money where his mouth is. Where does A go? A goes to R to S, C. Done. C goes to R to S, B. Mess this up. There are A's, B, C. Yeah, I think I messed up the first one already. Let's see where A goes. A goes to R to S to C. Around, let me follow something, see if I can. A to C, C goes to R, to S, B. Okay, we're gonna have to come back to this. Let me try the other one on my notes, see if it works. Can't believe I missed that one. Let's try this one first, shall we? A. Anyway, A, B, C, D. And CCA. So we'll see what happens here. See if I got it right this time. D goes to R to S, C, R, S, B. There we go. Oh, I'll stop here. A goes to B. B goes to, where does B go? Goes to R, S, A. So it's closed off there. And let's see, where does C go? C goes to R to S D is done. D goes to R, S, C, this done. Now, of course, we need to check the R and the S part. All right, make sure nothing happens there. R goes to S, C, back to R, S, C, back to R, to S, to A, back to R. Thank goodness. And this means that SS will work out, but we need to check it. S goes to A, to R, to S. So the other one, my notes is wrong. I will correct that for you next time. And I will give you one last lemma. We'll work on this. Check other. That's really more of a command to me. 12. Here's the last lemma that we'll build up to next time. If n is a normal subgroup of AN and n contains a 3 cycle, then n equals AN. And here will be inverted battery. Better than 3, and n contains a 3 cycle. Actually, if you think about it, this is a really strong statement, because what it says is if you have a normal subgroup of AN, at first blush versus, in any normal subgroup of AN, all you need is for it to contain 1 3 cycle. If it's normal, it has to contain all of AN. Okay, we'll pick it up there tomorrow, or well, Wednesday. Any questions? Any questions? Okay. I will then see y'all later. Any questions out there? All right.
No, thank you.
Until next time.